In calculus, finding the highest and lowest points of a function is crucial for optimization. These points, known as local extrema, occur where the function transitions between increasing and decreasing. Today, we will learn two powerful methods to identify them. Before testing for extrema, we must find critical points. These are values of x where the first derivative is either 0 or undefined. These candidates represent locations where the slope of the tangent line is horizontal or the function changes behavior abruptly. The first derivative test examines the sign of the slope around a critical point. If the derivative changes from positive to negative as we pass through x equals c, the function climbs then falls, indicating a local maximum at that point. Conversely, if the derivative changes from negative to positive, the function is decreasing and then begins to increase. This transition creates a valley, which we identify as a local minimum. If the sign does not change, it is not an extremum. Think of it as hiking. If you are walking uphill and then suddenly start walking downhill, you must have passed the summit. This simple change in the direction of the slope is the core logic behind the first derivative test. The second derivative test offers a faster alternative by looking at concavity. Instead of checking signs on both sides of a point, we look at the curvature exactly at the point where the first derivative is 0. If the first derivative is 0 and the second derivative is negative, the graph is concave down. Because the curve is frowning or curving downwards at that horizontal tangent, the point must be a local maximum. If the second derivative is positive at a critical point, the graph is concave up. This smiley shape indicates that the slope is increasing, meaning the horizontal tangent line sits at the very bottom of a local minimum. Let's apply this. For the function f, x equals x cubed minus 3x, we first find the derivative, which is 3x squared minus 3. Setting this to 0 gives us two critical points x equals positive 1 and negative 1. Testing x equals negative 1 with the first derivative test, we check values nearby. At x equals negative 2, the slope is positive. At x equals 0, it is negative. The change from positive to negative confirms a local maximum. Now let's use the second derivative test for x equals 1. The second derivative is 6x, plugging in 1 gives us positive 6. Since the result is positive, the function is concave up at this point, confirming a local minimum. Note that if the second derivative equals 0, the test is inconclusive. In such cases, you must revert to the first derivative test to determine if the point is a maximum, a minimum, or an inflection point. To summarize the workflow, start by finding the derivative and solving for 0 to locate critical points. Then, choose the test that is easiest for your function, either checking the slope sign change or the function's concavity. The first derivative test is more universal as it works even when the second derivative is hard to calculate or equals 0. However, the second derivative test is often faster for simple polynomials and trigonometric functions. Let's try a quick practice. For f, x equals x squared minus for x plus 5, the derivative is 2x minus 4. Setting this to 0 gives us a single critical point at x equals 2. The second derivative is a constant positive 2. Since it is positive, the function is concave up everywhere, meaning our critical point at x equals 2 is a local minimum. Plugging x back into the original function gives the coordinates 2, 1. Mastering these tests allows you to sketch curves accurately and solve complex optimization problems. Remember to check your critical points carefully and verify with concavity whenever possible. Thank you for learning with us. Generated by Vision Solve AI.